I read this
I
one.
got that. There's a point where I was like.
I thought they'd be different.
About like.
All right.
To do like.
First order of business today is we need to discuss the upcoming schedule because I'm going to do something that I have not done in 7+ years of teaching, and that's cancel a class.
Oh, wow.
I know.
Is it too late for a refund?
So I have to cancel this Thursday's class because it is the meeting with the professional advisory board. And as just about the only person who has implemented anything related to an AI policy and they're interested in AI policies, I have to meet with them to tell them what I have done and to get some of that feedback, because also the university president will be there and the department will look very bad because no one other than me has done anything with regards to this and I have the only data. So I'm kind of holding my department hostage in that regard.
Your boss canceled.
That's their fault.
It is their fault. If they were doing more, then I wouldn't have to cancel class. So if you're frustrated about that, complain. If you're not frustrated about that, go party.
So I'm assuming we're no longer having the exam next Thursday since we don't have school on Tuesday. No Thursday, no Tuesday.
Yeah, so that is the second half of this, is that Veterans Day is next Tuesday. So I either need to get you a study guide for next Thursday, but I want to have some kind of review for this. So either what that means is review next Thursday, exam the following Tuesday, or it means we forego that and people come and review with me in office hours or come to me with questions and then we can take it on Thursday.
So, are we expected to have 2 more exams or is it 1 more exam?
I'm kind of thinking at this point, it's basically an exam and a final. My original goal was to divide the class into thirds.
Yeah.
And we're closing in on the 2/3 point, especially considering how empty. The fact we're missing a day due to Veterans Day, we're missing a day due to Thanksgiving. So we're pretty close to 2/3 of the way through.
Are we not over then? Like, cause it's week 7 of 11 and
Right,
with those days gone, we're like almost over the 2/3 mark.
yeah. So that's why I'm thinking that I want to have an exam sooner rather than later to try to equalize the amount of content that would be on this exam and the third exam.
Okay.
The more I put that off, the more content is gonna end up on that second exam, which wouldn't necessarily be ideal. But I have an idea of where I want that cut off to be, and that's after we finish this and finish probably one more day, so 2 more days worth of content. So I think it makes the most sense to have an exam a week from Tuesday. I think that's where it makes the most sense.
A week
Just
from
be
next
content
Tuesday?
stuff. Yeah, because we don't have class.
Yeah.
So it has to be a week from that, and that would allow us to have a review on Thursday as well.
So then study guide would be provided to us like by next Tuesday-ish.
Yeah. I would want to give you that week, so my goal will be to have it to you by the end of this week. Because if the class isn't meeting and I don't get that reminder, who knows how far down that task list it falls.
I'm sorry to hear that for you.
I would personally prefer to have you in class.
Yeah.
Because it's very hard sometimes to get into for class hours, especially because we're going up and stuff.
Yep.
So that's my personal.
Yeah, let's do that then, we'll tentatively plan, I don't necessarily want to completely lock everything in, but let's tentatively plan for an exam a week from Tuesday. And I'll get a study guide to you as soon as I reasonably can. At least within a week of the exam. And then we'll review next Thursday. I can also provide some practice problems potentially for people on Thursday as part of canceling class on Thursday. If we do something with regards to that practice, and then that would allow you to, since I won't be there personally, come get answers to that in office hours. But I can do that so that it's not a complete and total waste of a day.
And that's next Thursday, right?
It's this
Thursday.
This Thursday, yeah. I originally thought that I could get by skipping the PAB meeting, but everyone is telling me, you're the only one with data, you're the only one with ideas of what we're actually doing, please come.
And that just makes you
Please come
feel
make us look good.
horrible.
It's just like, I'm the only one doing work, it's really frustrating, but outside of that.
Yeah, or not gamble, you don't like that, but
Why not just pay somebody a fiver to just like represent you?
Yeah, there you go.
Yeah,
You do this.
That's probably a better representation of the department as a whole.
Yeah.
Yeah, and it's just specified.
Those are harsh words, Chris. Dude.
I don't wanna get too much into our department politics, but there were some requests for
Right in.
what we should do with regards to an AI policy. And one of those responses boiled down to, I'm aware of the tools that exist out there. We should have control over those tools rather than letting the students control us through the use of those tools. And that was kind of the extent of a response for an AI policy that,
I mean,
yeah, I don't know either.
Doesn't mean much.
No, that was paired with an, I'm not gonna be at the meeting that discusses this. Let me know how it goes.
Also, the list of tools has changed like every month for the last 2 years.
Yeah.
Like, it's not the same.
Yeah.
Even after the main proposal.
Yeah, the industry is very different. The jobs that we're preparing people for are very different. And because of that, we need to be incorporating learning how to use AI into our curriculum as part of augmenting a workflow. That needs to be in our upper division software engineering curriculum, and it is not. So,
just
yeah,
I already did.
anyway. Probably enough of class kills on on something else that I'm working on the side. But let's dive back into it, start to get through some of this content. It's like a fascinating conversation, I don't think, though.
It's class.
That's why I'm in class, dude. Focus on class. Actually, no, just start talking about random stuff.
I should name you both Unix and say, I feel seen, Unix.
Yeah, you would never say that.
Yours did.
He just did, unfortunately.
It's out in the world now.
He never actually tells his bad jokes, he just soft launches them every time.
Exactly. It's how to rally a class around you. You make everyone facepalm and then they pay attention.
You know the SpongeBob episode where they've got pitchforks?
He proves me wrong
around-
immediately. You know how to rally someone around it?
I think it was tied to rally.
Yeah, I think he's talking about forming a mob against you.
That probably works.
Said pitchforks, we said classes for it.
So at the end of last class, we were talking about exact inference and Bayes nets. So as a refresher, what was a Bayesian network?
What was it like?
Is there in a graph?
What was one more time?
What was a Bayesian network?
Oh.
Or Bayes net?
Something about conditional probability and independent variables.
Yeah, so we want to represent a joint probability distribution, which is a probability distribution over a number of variables. And so we need probabilities for every combination of those variables. If we have 5 variables, then we need, this is true. Variable 1 is true, 2 is true, 3 is true, 4 is true, 5 is true, 1 is true, 2 is true, 3 is true, 4 is true, 5 is false, etc. And that ends up being an exponential number of probabilities based on the number of variables that you have. So if you can show that there is some conditional independence between these variables, that allows you to separate this one massive 5-dimensional table into 2 tables, or 3 tables, or 4 tables, and you get closer to a linear amount of work compared to an exponential amount of work as you find those conditional independence. So we talked about how to construct a table, we talked about how to look at a Bayesian network and determine the associated probability, how to, if you were ordering them, how to order them in ways that made sense and made fewer total probability entries, how to order them in such ways that there were more and they looked gross. But the last thing we covered was exact inference. How do we actually do it? So the example that we used, we said, based on a particular observation, we find that both John and Mary called. What is the probability that a burglary occurred? And we were able to query the Bayes net to be able to determine that probability. And there were 2 ways that we could do it. We did find that the probability that a burglary occurred was 28.4%. Based on the associated data that we had collected. We could just enumerate, which is just summing over the entire probability distribution under which the constraints are met. So we hold constant, John called equals true, Mary called equals true. then sum everything else and determine the probability that a burglary was true over the probability that a burglary was true or a burglary was false, given that John called was true and that Mary called was true. So that's exactly what's happening here. We have our normalizing constant alpha times the probability of what we care about given the evidence, which means that we sum over every other variable. So y is, in this case, the probability of a burglary, earthquake, and alarm, given that John called and Mary called. And then we take all of those for which burglary is true, normalize that, and we have the associated probability distribution once we normalize the 28.4% true, 71.6% false. Does that make sense? As a refresher, does that seem like where we were? How are we doing with that? Do we get a sense of if I gave you something like this with a joint probability distribution or a Bayesian net on an exam, would you be able to answer a question like this? It's not necessarily showing it with this, but looking at the network and being able to figure that out from the network.
It's very second, but.
I saw one nod, one shake, and quite a few stares.
Practice it.
Yeah, with practice, that would be a little bit easier. Yeah, so if we look back over the Bayes net, let's actually, when is the last time we had access to that Bayes net? Here. Doesn't matter what else is on the screen, I'll actually give myself a little bit of room to draw. So we know that this happened. We know that this happened. So it doesn't actually matter. These are now factored out. These are our givens as part of the network. So we want to figure out what is the probability that this happened and was the cause for John and Mary both calling. So we know both John and Mary called. So we have to sum over every possible variable now that burglary was true, earthquake was true, and alarm was true. Burglary was true, earthquake was true, alarm was false, etc. Every other combination of that, given that we know that both John called and Mary called. So you would just iterate over all of that. It would become a sum of lots of terms, which is why we use the summation terminology and why we use our sigma to specify that. If you're not used to staring at math or thinking about math in terms of its programmatic concepts, I'll try to help with that. Whenever you see a summation, that's just a loop. So if the capital sigma scares you, just think of it in terms of writing a program that is a loop. If you see a sigma followed by a sigma, that's a nested loop. It helps to think of it in terms of programmatic representation, I find. So you just sum over every possibility, holding that these are constant, given that this happened. What is the probability of this? So this true, 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 false, false, true, false, false, over those same four, but with also false, false, false. So now we're holding it false, true, 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 false, false, true, false, false. So there'd be 8 total terms, 4 terms in the numerator, 8 terms in the denominator. Does that track? All right, rather than going through all this, we'll just go back there. No, this is really just stating mathematically exactly that same idea. The probability that X happens, the query, this X in this case is the probability of burglary, given the evidence. What evidence do we have? Both John called and Mary called. Makes sense that that is the evidence that we are using to try to determine whether a burglary occurred or not. When we have additional information, like my 2 neighbors called me, that is evidence, additional evidence for a burglary happening. The chance of a burglary on a given day was 1 in 1,000. But because both of your neighbors called you, the probability changes because of the evidence that you have.
I just want to try to understand, like the network can go like other ways, but so like you can say like, given that like Mary called and there was a burglary, the chance that John call,
Yeah,
you can do it that way too, so it's.
Yep.
Okay, I just
yeah,
wanna share.
any question or any evidence that you would want to use, or any question you'd want to be able to ask is just gonna change. What are your evidence variables and what is your query?
Okay, perfect,
Yeah,
thank you.
so you can answer any query that you could possibly want with this network, and a well-designed network will make most of those queries easier to answer, and a poorly designed network will make a lot of those questions harder to answer. You'll have to sum over more variables. You'll have to use more conditional probability, which will mean that you're using unnecessary space to store all of those conditional probability tables, because there will be more conditional variables, so you're just conditioned on more things. If that makes sense. The alarm was based on the earthquake and the burglary, but if you make the root of the network alarm, then it creates conditional representations throughout the rest of the network, such that now it's more complicated. But if you make John calls and Mary calls the two roots, then it actually ends up fine. But we will talk about that momentarily. So you can answer just about any question using this exact logic, computing the sums of products of conditional probabilities from the network. So this is what that looks like for the above example. So here is what would actually solve that problem. We start with the probability of burglary given John calls and Mary calls. We have our normalizing constant. We just ignore this for now. This is so that when we figure out that associated ratio, we scale that ratio so that the probability density becomes 1. We need the probability of a burglary, the probability of an earthquake, the probability of an alarm given burglary and earthquake, the probability that John calls giving an alarm, and the probability that Mary calls giving an alarm. We sum that over every possibility for earthquake and alarm. So burglary is the query variable, that's outside of the scope, so it's held here. Earthquake here, and then we just sum over every value of earthquake and alarm, because burglary is the query variable, and John calls and Mary calls, we don't need the probabilities of those, we just need the conditional probabilities. And you do this, you'll have an answer, you'll be able to generate this. So this is burglary, and then this is not burglary. So this is the probability of burglary, this will come out to some number. Then you calculate the probability of not burglary given, that's just 1 minus that. So if you don't have the alpha associated, then you calculate both and then normalize. But yeah, that normalization leads you here. Questions on that process? Does this make sense? How you would look this up in the network? The probability of burglary is just straight out of the network. That's 0.001. Probability of earthquake, 0.002. A given B, these are all just lookups in the table, and we sum them over everything that the alarm can take and the earthquake can take. So that's the exact inference process. So we do have those hidden variables, the earthquake and alarm, because we don't know if a burglary is happening at the same time an earthquake is, and we don't know that these are not the conditioned variables and they're not the query variables. So anything that's not the conditioned variables or the query variables need to be summed over. Questions on that? Does this look normal or calculatable? I never get a sense from looking at students whether this is.
You explain double sum, everything, all that made more sense.
Yeah, thinking of it as a nested loop, where you would say basically for each possible value of earthquake, inside of that scope, for each value of alarm, do this work. So this is going to be done a total of 4 times, because earthquake can take 2 values and alarm can take 2 values, true, false, true, false. Yeah. All right. Issue with that? Anyone want to take a gander? This is a pretty typical issue we see in this class and just in general.
I mean, if you have a really big net, like, that's a lot of calculation, right?
Yeah, what is the runtime for, like, what is the big O complexity of this in the worst case? I guess it's redundant to say big O and in the worst case.
It's exponential speed, n times n.
It is actually exponential because it's based on the number of variables in the network. How many hidden variables are there going to be? Those are all nests inside of your looping structures. So there are going to be a number of nested loops that's equal to your number of hidden variables. The more variables you have, loop inside loop inside loop inside loop inside loop. And we know when the variable is inside of that, that is the variable being in the exponent. If there are 2 nested loops and you can hard code that as 2, then you have something that's quadratic. If you have n nested loops, then that is exponential. So yeah, there are 2 to the n terms in the sum, each being a product of n probability values. So a naive solution is n times 2 to the n calculations, and that don't scale. If we're intelligent about this, we can actually get rid of the n. We move sums inwards because not every factor is going to be in that. So you basically are now choosing how you nest your loops such that you're not repeatedly summing unnecessary things in the same way, in ways that you minimize that amount of work, and that gets rid of the n, but it does not get rid of the exponential factor. So now we've moved the sum of the alarm inwards from the earthquake. So now it's the equivalent of, instead of putting everything inside of both nested loops, we factor out something in between the outermost loop and the innermost loop, which saves you doing that twice. But you can see how that doesn't remove the number of sum terms in there. And how even if you optimize this, it wouldn't remove the exponential complexity of how many sums there are in the problem. So in code, all you do is loop over all the variables in the associated order. Wherever you see a sum, you're going to define a loop over every possible value. Whenever you see something that is not that, the probability of this, that's just a lookup in the table. So loop, lookup, loop, lookup, 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 back, lookup, 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 back, lookup. Done. It's reading math and reading code shouldn't be terribly different, hopefully, but I don't think we necessarily teach it that way. But here's exactly what that looks like. We take the probability of B, and then we need to loop over everything from E. And inside of that, we have another loop that goes over all possibilities of A. And then each lookup is just a straight path from there instead of a branching factor. So whenever we have a sum, we have to ask how many values can that take on? That's the branching factor at that particular node of this tree. Same here. We branch over that, and then whenever we have lookups, we just have tests. So you can kind of see how the complexity bakes into this and why it is exponential in nature, because we have we have 2 different layers of this tree where there is a branching factor that's not 1. And as we introduce more and more variables, that's more and more levels of this tree with a branching factor, which leads to an exponential scaling of the number of leaves. So here's kind of a way of showing and looking at, here's what that lookup would look like. So this probability is going to be this times this times this times this times this, plus this times this times this times this times this times this, plus etc. That's the associated probability. But then we need to normalize it. So we need to sum that over the probability of not this. So you would have the numerator are these 4 paths. And then if we have the probability of not B, then that's 0.999. So we're going to take these 4 paths that exist in this tree, we're gonna divide it by those same 4 paths. Plus the 4 paths. Of not B. So instead of doing this, you do that and then sum the same exact stuff. And that ratio, when scaled to have density 1, is what gave us the probabilities on the other slide. Because this now sums over everything we care about from both burglary and not burglary. So the probability of burglary is just the probability that one of these paths happened over one of these paths happened plus one of these other paths happened. Because we know John called and Mary called, so we don't ever have to care about Mary not calling or John not calling. Notice how nowhere in this is there a not M or a not J, because those are evidence variables. We don't care about those values because they already happened. But we don't know anything about whether an alarm was triggered or not. We don't know anything about whether an earthquake happened or not. And so we just need to care about what is the probability that a burglary happened over a burglary happened and a burglary didn't happen, given the information that we have, which is that John called and Mary called. Questions?
This is only a fraction of what our possibilities are.
Yes, and the idea is that that's because we know that both John called and Mary called. If we had to sum over those, we'd have twice as much. This would be twice the size.
Yeah.
And we also know that that burglary is held constant because we're asking what is the ratio of burglary to not burglary.
It seems like there's supposed to be.
This is everything we need. So if we say what is at this path, what is this path telling us? We know that a burglary happened, that an earthquake happened at the same time, that John called, and that Mary called, and that alarm happened as well. So I should put that here. So that's what this node is saying. This is these 5 combinations. Then here, the only thing that changes is that the alarm didn't happen. So this is burglary, earthquake, not alarm, John, Mary. This is, now we have alarm happened, but earthquake didn't. So we have B, not E, A, J, M. And here we have B, not E, not A, J, and M. This is the equivalent of summing over the earthquake and the alarm. So we have earthquake and alarm, earthquake and not alarm, not earthquake and alarm, and not earthquake and not alarm. We don't care about John and Mary because they're held constant. We do need to factor that into the associated probability, but we don't need to have not John and not Mary because we know they both called. So the only thing that we need to figure out is the ratio of the probability of these 4 destinations to the 4 destinations where we would negate the B, negate the B, negate the B, and negate the B, which is what these 4 paths are doing in the denominator. So we actually don't, if you do this ratio, you don't need a normalizing constant. If you do the 4 paths to the ratio of the 4 paths without B, then you need the alpha to handle that. But if you do the division here, then you don't need the normalizing constant. So it's either this ratio or that division. Either one of those will work. This denominator builds in that scaling constant. Really good clarification. Does that help things make a little bit more sense? So it's really just a bunch of lookups into the table and about which variables are we summing over. Anything else before we move on? Great, we'll move on. So the procedure we're gonna use to do this in pseudocode is going to be called enumeration ask. So here's some pseudocode that if you implemented this, you would basically be able to do what we just did. We're gonna have the same exact, the query variable, the evidence variables, and then that will return the associated probability distribution over all of the non-query, non-evidence variables. So inputs, we take the query variable, this was burglary. The evidence variables, this was John calls and Mary calls. And then the associated Bayesian network. And then from those three inputs, we just go through the process of summing over every value. So distribution over X for each value of X, this is the burglary or not burglary. Call enumerate all, that's gonna go over all the associated variables that were not this query variable and this observed variable. And you just have a recursive definition for that. So instead of thinking about it as a loop, this just does it recursively. And as we've shown in past classes, whenever you have loops, you can write recursion. Whenever you have recursion, you can write loops. Doesn't really matter which, except for some runtime analysis. And we can show that the recursive version is slightly more efficient than a looped version. Of course, there's an inefficiency with this as well. Can anyone identify it? Any guesses? What is this doing unnecessarily? That's why it's called a funny bone. It's funny to me.
Just continuing to feel like
It's in the second function. Oh.
So the multiplication that's being done here is not being stored anywhere. So we're recomputing multiplications every time we query those multiplications. So yeah. Yeah, whenever you see an efficiency in something that has loops in it like this or repeated recursion, it's usually that you should be storing something as you go. So what do we do about problems like this? What is the algorithmic solution to computing something over and over and over and over again? Yeah, what is the algorithmic term for caching in the lookup table? Program. That's the second word. Dynamic programming, indeed. So we have a dynamic programming. If we embed dynamic programming in this, such that when we compute the value of one of these multiplications, we store it in a table for later lookup, and then we first ask, is this in the table? If not, then look it up. We can go from an exponential complexity algorithm to a polynomial time complexity algorithm. So enumerate ask with dynamic programming is the right way to go. The next thing we might want to do is figure out when can we eliminate some variables. And we can show that the way this is done is we can calculate combinations of variables in ways that make this more efficient so that we can bake out the repeated calculation. We know it's not there. So here we're going to relate what we just looked at in terms of some factors. We're going to call them factors. So the probability of B is F1. That's a factor. Probability of E is a factor. A given B and E is a factor, and J given A is a factor, and M given A is a factor. They take the associated query variables that they depend on. So we could represent each factor as a matrix. And I know that sounds scarier than it is, but to give you an idea of what this might look like, the fourth factor over A is just the one-dimensional matrix of John given alarm as the first cell and John given not alarm as the second. So it's just the aspect of the Bayesian network, one of those conditional probability tables, but represented in matrix form. So if we store all of these factors in their associated matrix form, then we can utilize some matrix computation and try to understand when we can combine some factors and reduce the amount of matrix multiplication that we end up doing. I did not close that parenthesis, that is bad. So we would end up now just replacing each one of these with their associated factors. And we'll talk about the pointwise product here in a second and how exactly we calculate that. But we end up being able to calculate a new factor when we can sum over something. So now we take out the sum over E, and now we have a new factor that represents the solution to this, but summed over E as part of it. So this is going to end up being less work than the entirety of what's above by calculating a middle point new factor and embedding the earthquake variable into that factor. So we sum out alarm from the product of F3, F4, and F5 to give us the new 2x2 factor F6. So instead of being a single dimensional table now, it's going to be a two-dimensional matrix where we now have multiple features embedded within it. And I don't know how dynamic programming is taught, but did anyone use the matrix multiplication example or the chain matrix multiplication example for learning dynamic programming? Does that sound familiar? It's out of the Corman book that you use.
So I remember it from algebra.
Yeah,
Otherwise, in doing it in, the only time I think I've done it was for an off-course that wasn't great, but CS degree that was
okay,
electrical engineering.
that makes sense. So the basic idea of this is that, let's say you need some chain of matrices multiplied together, and the order in which you evaluate that, the question is, where do you put the parentheses to say which matrices do you multiply first? When you multiply an inner matrix by an inner matrix, you get a different sized matrix. And depending on what that is, it can be a smaller matrix or a larger matrix. If you make a larger matrix and then try to multiply that by things on its side, you end up with more possible calculation. So there's kind of an order of operations to matrix multiplication where you look at the form and then try to minimize the total number of matrix multiplies that you do. And you can be off by many factors of 10. You can do this incorrectly and have 10,000 times more work than if you do it correctly, just to arrive at the same answer. So this helps with that idea where if you intelligently create new factors out of this, you can reduce the total amount of work that this is in a large scale network by correctly identifying when you can put some matrices like this together into a new factor that creates a smaller matrix rather than waiting for a larger matrix. And that ends up saving you a lot of computation over time. So now if we represent the entire computation, we have just F1 times summed over E, F2 times F6. And that will be better than if you left all of that in there and multiplied them in a different order. That may create factors more work for you than an analysis that minimizes that. So that's just something to be aware of whenever you're multiplying matrices. If you can analyze it in advance, you can save yourself some work. We can continue to do this, summing out E and making a new factor. So here is the new factor F7. And that just leaves us with F1 times F7. And that as a multiply is not that complex. So the underlying work that you did made this last computation the easiest that it could be. And we'll talk about what a pointwise product is, or how you can actually take this and turn that into the associated answer. So this is the other way to do it other than just brute force going through it, because this will save you some of that brute force work in larger networks. So what can we do? How do we make these operations on these factors to minimize the associated amount of work? Was there any question on the last slide before I move on to this? All right. This will hopefully make this make more sense. So what can we do with factors and how does it save us work? So we have two factors that have some variables in common. We'll use an example where there are just 3 variables. We use 2 factors and they share one of those variables. So here's an example of that. We're taking the multiplication or the cross product, I guess, of we have 2 factors that combine variables x and y and their associated values, and y and z, or I guess h, g has y and z, so that the end result of this is some search space over those 3 variables. If we're doing this in terms of straight looking this up, then we have to do xy, xz, yy, yz, and there's repeated work in that process. So we can see that if we actually write out the associated probabilities, that rather than doing a full cross product of this, where we'd have to take a particular value for x and y and a particular value for y and z, we can factor out the y and just look at it in terms of a 3 variable system where we want to be able to calculate h of x, y, z, which is going to be the value of x, y, so true, true, and the value of true, true to get us true, true, true. So that's just the 0.3 times 0.2 gives us 0.06. But note how the values for y here are different. So we would have to fully enumerate what happens if y is true here and y is false here. Y is a single variable, it can only have 1 value. So that's what we're factoring out, is that we're forcing y to only ever have the same value, rather than what happens if y is true in the first one and y is false in the second one. So where does this 0.3 times 0.8 come from?
Y is true, you're forcing it, right?
Yeah, so this xy has to be x is true, y is true. There's no reason to consider anything from y is false here. Y must be true, z is false. That gives us 0.3 times 0.8. So this is a way of constructing this table without the repeated work whenever some of these matrices would share a variable in common. We just factor that out. That's what creating those factors do, is it squishes the same variable down into a single dimension rather than trying to treat it as 2 separate dimensions. Because it can't possibly be 2 different dimensions, it's the same variable, it has to have the same value. So whenever you have something that is size 4 cross something that is size 4, you would expect there to be 16 variables. But because we don't have to consider any of the times when y is differently variable, the answer is only 8 instead of 16. So we have 8 calculations to do instead of 16 calculations. And this is just when we have 2 variables, or two of these vectors, and one of them shares 1 variable in common. There's no reason to consider that. So we can factor it out. Questions on how that saves us time, how that saves us work, and how it allows us to create the different tables based on the associated input values? Dots all over the place, I have to see them. Anything I can explain in better detail? So that's the first thing. So let's talk about what it means to sum out a variable. So now we have this table X, Y, Z, and maybe we want to sum out a value from that. So what does it mean to sum out X? We take this 8 probability list that we have, and we can turn this into 2 matrices. The first matrix is where X is true, and the second matrix is where X is false. And if we sum out, then we just sum the associated cells. It's just matrix addition. And we now get a 2 by 2 matrix where we have the values of Y and Z without X. So when I said sum out from before, that's really what that means. Just saying we don't care about that variable anymore. So when we query now just Y and Z, we only need to see Y is true, Z is true, which is the sum of X is true, Y is true, Z is true, and not, sorry, X is false, Y is true, Z is true. Draw that out just to be sure. This is X is true, Y is true, and then this is, and Z is true. This is X is false, Y is true, Z is true. So if we want to represent Y is true and Z is true, it's just going to be the sum of X and not X, holding Y and Z constant. That's going to be true for each one of these pairs. So we just sum that up, and now we have an associated matrix without caring about X. We don't care to split it apart into when X is true or X is false. And that will help with a query that has nothing to do with X.
Yeah, so when you say summing out X, it's literally just like, it's not relevant, so we just take all instances where it occurs and you're adding it, okay.
Yep. Yeah, but if we turn these into matrix operations, then we can utilize matrix processes to improve the speed. But you can basically just think of it as looping over every possible value of X and adding them up together to get YZ. And that's true for every other cell here, just holding, this was X is true, Y is true, this is X is true, Y is false. Not X, Y and Z, not X and Y. I'm tired. So just like before, anything that's not involved with the variable can be summed and moved outside. So we have the ability to do something like this. Does it make sense what's been done? We just moved the summation inwards because, well, rather, we factored out G of YZ because it has nothing to do with X. There's no reason to sum over X for values that don't vary in terms of X. This is a function that has to do with Y and Z, not X. So do it once rather than do it for every possible value of X. That saves you work. Just like how matrix chain multiplication works, if you do this intelligently, then you can save yourself many factors of work. Again, it does not ever take the exponent out of it, but you can significantly reduce the amount of work that it takes by intelligently making these matrix multiplies much, much smaller. The matrix multiplies from a past slide by breaking this apart and turning it into an addition. So we get a new elimination ask where we don't necessarily multiply the matrices until we need to sum out a variable from them. And that, again, optimizes the runtime. Questions on the entire thing as a whole?
Is there perhaps like a representation of the matrix that shows like each X, Y, inverted, not inverted, and how it's equivalent, like element wise, what it would look like as variables, and then it would look like as the matrix representation?
Yeah, that was kind of here-ish. Because you would see this as part of your conditional probability table. All the X, Y, and Z in this case are just conditional probabilities. So if you're trying to represent them summed out or saying like, we don't care about alarm, we don't care about John calls or Mary calls, something like this, then that's what gets factored out when you're doing those conditional probabilities. That's why you're asking for an example that I don't really have drawn out at this stage, but you can envision this being back in that associated Bayesian network where the question would ask you for this. And in order to do this, now you either have to go through what we drew out before when we did this, not this. Even before this. That. When we went through this whole process, you can imagine in a larger network that this is a big question to ask. If there are, instead of 5 variables where there are 2 evidence variables, if there are 100 variables and there are 30 evidence variables, so something like the insurance network example from the last class, then the sheer amount of work that you have to do is a significantly deep tree with a very large branching factor. And that's going to involve a lot of calculation, a lot of matrix multiplication in ways that create very large matrices that need to be multiplied together. And the idea is that with exact inference, you're going to run into a very big time wall when you do that. And if you use the variable elimination, then you can get rid of a good chunk of that work. Possibly turn it into, from the amount of work that exact inference is, you could turn it into 1/10,000th of that work, or 1/100,000th of that work. You can't eliminate the exponential nature of it, but you can go from it taking a week to complete to it taking a few hours. And if you're in a workplace environment where you need answers and you need them fairly quickly, taking most of a workday is not too bad. Taking a week is going to be a problem. So if you can reduce it by a large scale factor like that, then it can be brought into a typical workflow or a reasonable industry size problem. That's not exactly what you asked for, but I think hopefully it helps to justify why it's worth going through the variable elimination and seeing how P of B could be X, P of E could be Y, and etc. We have things that depend on each other. Other questions? Yeah.
Could you explain again the block we're doing like one step versus the other in the next 2 slides where you're factoring out X with or you're factoring out Y in the next one and the one after that where you're doing the.
Yeah, so this entire question we're basically turning something like this into a factor. Where instead of having to do this repeated a bunch of times, we're just reusing a factor. If we had a way of bunching these up into a single node, then you're reducing the amount of work by querying that factor instead.
Right.
And you could calculate this entire distribution, and this now becomes that sum where if this is a variable that we don't care about for some reason, then we could accumulate and turn that into another factor that just says, we're going to sum this and that, throw it together, this and that, throw it together. And now when we get to this node, instead of having to do this depth first search at this level, then it's less work than that. And this wouldn't be the case if this is just represented as nodes, but when this becomes matrix multiplication, then depending on the order in which you do this, it actually can save you factors of work.
Right.
Really good question. Yeah, does that help?
Was there a difference between when you were factoring out Y in the next slide and then when we were doing the X and not X in the slide after that?
Yes. So factoring out. So yeah, factoring out is just the idea of taking a variable. I guess it's probably easier to see from here. The table. Factoring out is just saying that we're going to represent this now instead of it saves the work of computing h of x, y, z based on, so the inputs that we have are f of x, y and g of y, z. We want to calculate h of x, y, z. We factor out y from that because we don't need to double count it. So that turns this from a 16, you have to loop over things 16 total times to come up with probabilities to doing it 8 times.
difference though with the next one, though? What was the next one?
Yeah, the next one is kind of going the other way, when we want to now represent h of yz, factoring out the x, not factoring out, but summing out the x. Now we can generate h of yz by saying we no longer care about x. So sum, take the values of x is true, given y and z, and not y and not z. And then not x, y, z, not y, z, not z, y, and not y, not z. And then that gives us the table for y and z without considering the x. They're kind of reverse procedures of ways for you to calculate a cumulative version given the components without ignoring ignoring the overlap between those versus factoring, stop saying that, summing out the x so that you have the ability to see just the table for y and z. If that helps.
Can you go back to the previous table real quick?
Yeah,
Just want to know.
yeah.
So. Are we assuming that there's an and condition between X, Y, Z? Is that what we're doing?
So yeah, we have these two tables. We have the value of when x is true and y is true, here's a particular outcome.
Yeah.
When x is true, y is false, here's a particular outcome. When y is true and z is true, here's a particular outcome, etc. So if we wanted to find when x and y and z all have their associated values, but this is the only input that we have. Because remember that we have conditional probability tables in a Bayes net. This would be so much easier if we had the full joint distribution. We could just query it and be done. Yeah.
Second, they were justifying that Y is true and Z is false, and still evaluates to 0.3 times 0.8.
Yes, so this is x is true, y is true, and z is false. So we look up x is true, y is true, getting the 0.3, and we look up y is true, z is false, getting the 0.8.
Yes, okay, that's what I do, because
Yeah.
I'm wondering why, the third row is not correct, like 0.9, it's not correct, because I didn't map it when I was scanning them through.
Yeah, we never need, if y is true, we're never gonna consider these rows. So we go true, 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 true. Without ignoring, and we ignore that. Here y is false, so we only look at these two and not these two.
Yeah.
And so it generates 8 cells instead of 16 cells, because y can't differ between the two inputs.
I get that, but I was just looking at when X is false and Y is true, and it's 0.9. When Y is
X is false, y is true here.
no on the left hand side, but we were
Here.
referring to our point.
Yeah,
It was just on, I wasn't analyzing it wrong, but it makes more sense now.
yeah. When we do this, we're only ever considering where y is true here, the 0.2 and the 0.8. So we get 0.9 times 0.2 and 0.8 over here, and never consider the 0.6 and 0.4.
But that would fill out the second. That's where
Yeah.
I was kind of, I needed the refresher.
Yeah. How we doing? Other questions? Let's quickly find where we were. It is 4 o'clock already. We should probably take a bit of a break.
Brain looks like a zombie, right?
Yeah, we'll come back to this in 5-ish minutes. Let's try to keep it to about 5 minutes because I still want to get through a good bit more content, but we'll come back. All right. We are back.
So. Yeah.
Last thing we're doing with regards to this before we transition is just a quick discussion on variable relevance. Because ordering your variables actually matters here. So let's, as an example, take the query, what is the probability that John calls when a burglary is true? So the first step to doing this would be to write out the associated nested summation, and I'm gonna pause for a second and see if we can do that. So let's take a couple minutes and see if you can write out a summation of probabilities that answers that query, given the same Bayesian net that we've been dealing with. This will be a good exercise in how much sense sounds like. So what's your query variable? What are your evidence variables? What do you need to sum over? Everything that is not those. How inwards can you make those because of the associated conditional dependencies? How can you minimize the associated amount of work? Anyone have questions on getting started? What's the query variable?
What's the probability John calls the game burglaries that John calls who's true or the burglary is true?
Kind of. So yeah, we want the probability that John calls and burglary is true over the probability that John calls and burglary is true plus John calls and burglary is false. So the query variable is John calls. The evidence variable is burglary, because we know that burglary is true in this case. So the evidence variable needs to be summed over to get that ratio. One side of the ratio is burglary is true, the other side is burglary is false. And then we know that, sorry, John calls is true, John calls is false. We hold burglary is true, and then look at every other combination of variables. But we want those to be in the associated level of the Bayesian network. So the first thing we should query is earthquake. Then we should query alarm, then we should query Mary calls. Because if we try to start with Mary calls, then we have to care about every other value of each variable. So we want to factor out as much as we possibly can. Mary calling will depend on everything, so that should be the most inner aspect. So here's the solution. Earthquake is at the very beginning, so that needs to be the outermost loop. Inside of that, we sum over every value for alarm, but we know that since we're holding burglary constant, we don't need to sum over burglary. We know that burglary is true and the value of earthquake that we have from the associated summation times the probability that John calls given alarm, but since John calls is the query variable, we only set that to be true. And don't worry about what happens if John doesn't call. Inside of that, we have Mary calls, given that the value of the alarm that we used in that summation. Make sense? This minimizes the associated amount of work and follows the associated logic of the Bayesian network that we've been looking at for a couple class periods now. And that would give us the associated ratio. Once we sum that out, we would be able to get the full probability of when a burglary happens, what is the probability that John calls? So this question asks, what is the value of the sum over Mary calls given Mary calls given alarm? What is that value? Think of it as the sum. What is that sum? What does that evaluate to? There's a result to this that hopefully becomes apparent as you think about it. There are two options. Given that an alarm happened, either Mary calls or Mary doesn't call. What is the sum of those two probabilities? 1. Yeah, it's 1. Because Mary can either call or not call given a particular value of an alarm. So the probability John calling is actually completely independent of whether Mary calls or not. John does not care about Mary calling. That does not influence John's calling or not. John calls whenever the alarm goes off, and the alarm goes off when there is a burglary or an earthquake, or sometimes just randomly on certain days. But John is not conspiring with Mary, so there's no reason that this is going to affect the actual probability here. So we can cancel it out. We don't need to include summing over variables that don't have relevance to the query. So any leaf node that's not either an evidence or query variable that is also a leaf node is going to not be part of this query. If we look back over the associated network, Mary calling was a leaf node. And everything that we cared about was John calling. So the network's flow is going to go from the burglary / earthquake through the alarm all the way down to John calling. And none of that is going to filter through Mary calling at all. If we just chopped off that node and got rid of it, Mary calling, we only have one neighbor and it's John. The answer to this question, John calls given burglary is true, is the same answer whether or not Mary's house has been nuked or not. Whether Mary never moved in or not. Mary is an irrelevant variable to this. So there's no reason to consider it, even though it's not a query variable or an evidence variable. Does that make intuitive sense? What's fun? Question?
Well, I'm just confused as to why the probability that Mary calls given alarm is 1. Like I can understand like the probability that she would call given all the circumstances is 1. Is that what that's saying?
It's a conditional probability. So ignoring why the alarm is going off, because Mary calls based on the probability that Mary calls is only based on an alarm going off or not. She doesn't know whether it was a burglary that set off the alarm, an earthquake that set off the alarm, or just the alarm going off for no reason. A false positive, some kind.
So it's just like the
So-
stuff of all calls.
Let's say today an alarm is going off.
Yeah.
what is the probability that Mary calls? You have to come up with a value.
Yeah.
What is the probability that Mary doesn't call? 1 minus the probability that she does call.
Yeah, yeah.
So the sum of Mary calling and not calling, given that an alarm is going off, regardless of why that alarm is
Gotcha,
going
okay.
off, because it's conditionally independent from that, has to be 1.
Gotcha, okay.
Good question. When you remove a leaf from a Bayesian network like this, it creates a new leaf. And that new leaf may also not be relevant to the associated query. So you can loop this process and eliminate any leaf node that is not a query or evidence variable. Look again, any leaf node that's not a query or evidence variable, remove, continue to loop until you don't remove anything. And that will make the network and the associated variables that you need to sum over fewer. So we can go through what is called a variable elimination algorithm to remove those variables before we even try to sum over. And what that does is it decreases the size of the exponent by 1 every time you do that, which is a very relevant thing to be doing. It's taking a cubic function and turning it into a quadratic function. It's taking, I mean, it's not removing the fact that the variable is in the exponent, but going from 2 to the n to 2 to the n minus 1 is halving the work. If you do that twice, it's a quarter of the work. If you do it 3 times, it's an eighth of the work. So anytime you can't eliminate this will reduce the size of the problem by a factor equal to a base of the exponent, base of the function. All right. We've seen that exact inference depends completely on the structure of the network, and the structure of the network can vary. In some cases, the network is nice. In some cases, the network was really ugly. So we can phrase this problem in terms of a generic idea, where if we have what is called a polytree or a singly connected network, we query any particular 2 nodes in the network and we ask how many paths are there from the higher up one to the lower down one. If there is 1 path and only 1 path, then it is a polytree. So going from earthquake to John calls has to go through alarm. So a polytree only has 1 of those paths. What's nice about this, depending on the size of the network, polytrees have linear time and space in terms of the conditional probability table entries. And if you have annoying multiply connected networks like the insurance network slide from before, then if you query a source node and a destination node, there may be multiple paths and ways to get there, and that can be exponential in terms of how far apart they are in the network, depending on the associated branching factor. But in general, inference is NP hard. If you can turn it into a polytree, then we can find inference in polynomial time because of the speedups that we've talked about. But if you do not have a polytree version of a Bayesian network, then yeah, good luck. It's exponential complexity best case. You reduce that to the 3-sat problem to show that it's NP hard. I don't know if people have gone through NP completeness proofs or NP hard proofs in any of your other classes. Anyone seen those? Reductions? Little bit, somewhat, long time ago, galaxy far, far away.
Did, and I brain dumped it already.
The basic idea of NP completeness is that there's this class of algorithms that if we could show that one of them has a polynomial time deterministic solution, then all of them would have a polynomial time solution because we have polynomial time conversion algorithms between one and the other. So I'm one NP complete algorithm, each of you are some other NP complete algorithm. I just have to be able to convert my representation to your representation in a polynomial amount of time. And if I can solve me in a polynomial amount of time, I use that conversion. And polynomial plus polynomial is polynomial, so I can solve each and every one of you as soon as a solution to me exists. As soon as a solution to any of you exists, we take that associated network that is polynomial time conversions and just convert from one problem to the other. We've solved them all. So NP complete is a class of algorithms that have polynomial time solutions via non-determinism and have exponential time solutions with regards to a deterministic solution, but we've shown that they all have some kind of polynomial time conversion algorithm between themselves. An NP hard problem is one that is at least as hard as an NP complete problem. It may be harder than that, but we haven't been able to prove it. So the idea is that the best case scenario here is that it is exponential in nature in general, until we have some kind of solution to the NP completeness problem, which is probably never coming. More theory behind that, take compilers. Or be David, who's taking compilers already. So another thing that we might want to be able to do with Bayesian networks is be able to compute the associated probabilities for every variable in the network. Posterior is just the conditional probability. So we want to be able to compute every single conditional probability within that network. And that's going to be a linear number of queries. And even in a polytree, that's going to be linear in nature. This gives you quadratic runtime. But we can reduce this to linear if we use clustering. So we can take, let's reveal this so that as I talk about it, you can see. Here is an example of a problem that utilizes a Bayesian network for whether it's cloudy. Based on whether it's cloudy, we have conditional probabilities for a sprinkler turns on and it rains separately. And then based on whether the sprinkler is on and it's raining, then we can determine whether the probability that the grass is wet. So you can combine the sprinkler and rain together in a single conditional probability. So you get sprinkler and rain given cloudy, rather than just sprinkler given cloudy and rainy given cloudy. So this clusters them together and then can save some time in lookups if you do this intelligently. So this turns what would have been an exponential complexity problem, because it's not a polytree, into one that is a polytree. Now granted, what's on the left right now is a polytree, but the idea is if you did have a more complicated network, you could join some of these nodes together, turn it into a polytree, and then you would have that linear time guarantee. So in general, doesn't fix the NP hardness of the problem, but does allow for some related speedups in larger networks. Questions on this? Again, a lot of this is just the big picture that's important. The exact details of this aren't terribly important. I don't expect that people are going to be remembering exactly how to do all of this 5 years from now. But if you know that there are speedups available and that can make a real difference, then you'll know I should look up what these speedups are so that I can implement. That's what I care about. All right. What about approximate inference? So we've seen that we have exponential complexity in the worst case for our Bayesian networks. So exact inference is going to be intractable for large networks. How can we create some kind of approximation for the inference in a Bayesian network so that we can get an approximate answer faster? We can do this by sampling the network. Who has used Monte Carlo simulation or Monte Carlo sampling before? What are we doing? Maybe?
We talked about Monte Carlo something before.
Yeah. Yeah, it definitely comes up. So basically,
A solution to that, though, I mean, I think it was one of the modifications that we could.
it was there's a word that sounded similar. It was not Monte Carlo. So Monte Carlo is the process of sampling. It's the process of saying, okay, we can set up this network as a simulation now, rather than something to query exactly. And given that we have a limited amount of computational resource, like let's say we can dedicate 2 hours to this, we're gonna set up the network as something that we can say, all right, generate a random example. So we start from the very beginning of the network. Burglary is either true or false. Use a random number generator and set burglary is true or burglary is false based on the probability of burglary. Similarly, do the same thing for earthquake. Then given the values that that has, combine those together and now sample alarm based on that burglary was false and earthquake was false. Now, is alarm true or false? From there, generate randomly based on alarm, whether John calls or Mary calls. And then you get a sample of an event that happened. This was a simulation of a day in the life of this Bayesian network. Then you continue to do this over and over and over and over again, given up to your limit of computational time. And that will simulate and get an approximate value for the answers to the associated probabilities. Are they guaranteed to be exact? Absolutely not, especially for rare events, which we'll talk about. But it at least allows you the ability to take on an exponentially large problem and say something somewhat intelligent about it. Yeah.
Is that different from the other Monte Carlo thing where you have time states and you only look at the previous one? Or is
That is, oh my gosh, why can't I, it's Markov chain.
Oh,
In fact, these ideas are combined significantly. We end up with Markov chain Monte Carlo, which is applying Monte Carlo to Markov chains. But
You like apply true randomness across the many simulation, or you?
that is a good question. And it's something that we have to address because something like the probability of a burglary is so small that even if I do this 1,000 times, the chance that a burglary is going to be true, we're only going to have one example on average where a burglary happened. We simulated 1,000 days, but a burglary only happened once. So what is the probability that John calls given a burglary? We only have a sample size of 1, even though we ran 1,000 simulations of whether John called given a burglary, yes or no. How confident are we in that answer of that probability? There was a sample size of 1, we shouldn't be confident at all.
But even like in a simulation of like, say you have a large sample size of like 1,000, right?
Yeah.
And how would you actually accurately use randomness, like without having some sort of bias? So
I don't know where the bias would come from. So you do it in the order of the Bayesian network.
like, say if you were like not just if we did something different, like say if we wanted to model like tsunami and how people react,
Yeah,
like it would obviously try to get higher ground.
Yeah.
Right, but what if we're modeled it where there is no higher ground? Like it says elevation, but change it to where the elevation is.
yeah. So you'd have to incorporate that into data collection or a network of some kind. So that we have prior probabilities or we have the ability to simulate that particular idea. You can't train something on something and then change a variable and think that it's going to transfer necessarily. That is a great point. And actually, you can use this in machine learning for transfer learning. So if you train a model on a particular data set, and then you change one of the variables in the associated data set, rather than retraining from scratch, you start with the function that was generated by the model on the initial set, and then that will minimize the amount of change that needs to happen from that function rather than starting from learning from scratch.
Because also like if we did this in like the penetrations testing environment, and yes, an AI.
Yeah.
Type of this, like the pen testers themselves are independent, but they probably wouldn't think like other people when they're attacking a system.
Yeah, interesting. So the question is, can you build a system that fully tests the associated probabilities of penetration or not, and can simulate what a penetration would look like? So that you can react and see what your system would do in that case. What is the probability that we correctly handle something given that a penetration has occurred? So you would need a complete model of the pen tester. You would need a complete model of the system so that you could accurately simulate how does this system handle the associated risk. So if you don't have the system and the ability to simulate the system, you can't respond.
Yeah.
But you could build an emulation of that system and then try to emulate that. What does the system look like when this happens? Well, it's emulate it happening, and that way you can then generate your data. Any other questions? So if you've taken math classes and seen confidence intervals, you know that confidence intervals are wider when we have a lower sample size and smaller when we have, or narrower when we have a larger sample size. So as we generate more and more and more samples, we can see that the confidence intervals surrounding the mean that we've seen so far, that should better and better approximate the true mean. It's never going to get there. A 95% confidence interval is never going to be size 0. It needs twice as many samples in order to have its size, twice as many to have its size, twice as many to have its size, twice as many to have its size, etc. So it can get very narrow, but you get a diminishing return on the value of new samples. So when have you sampled enough for the law of large numbers to kick in and for you to be reasonably certain that the mean of what you have seen so far accurately approximates the mean that you of the system? So you can't do exact inference, you have to use approximate inference. How much data is enough to make sure that you are confident that the mean of the data that you've gathered approximates the real mean? So 2 sampling methods. We can use a direct sampling method, or we can use a Markov chain, because Markov chains in Monte Carlo go hand in hand with each other. So we'll start with direct sampling, which hopefully is a bit of a refresher, but we'll go through it in case. So imagine that you're flipping a coin. On each trial, shows up heads or tails. And if we know that the coin is fair, we can determine the associated probability through enough trials that the coin is fair. So I give you a coin, you flip it, and after 10 flips, it's come up heads 7 times. Who wants to assert the coin is biased? That seems like a reasonably normal outcome, right? Yeah, it's expected. There's a reasonable probability that given a sample size of 10, that it shows up 7 heads out of 10. But now I flip it 10,000 times and it shows up heads 7,000 times. Who's asserting that the coin is biased? It should be everyone. If it shows up 7,000 times out of 10,000 times, that is so incredibly unlikely.
Yeah, but,
Because the law of large numbers is kicked in at that point.
yeah, but, I mean, it's not like it's a double.
Right, right. It just is weighted in some capacity to where it's more likely to come up heads than tails. There's more weight on the head side than on the tail side than the head side. So the tail side falls heavier, more likely revealing the head side. So yeah, if the coin is fair, law of large numbers kicks in, and the idea of an outlier having it show up 70% of the time heads goes away. It will be very close to the mean. The larger and larger the sample, the closer the bounds to the mean. Double the number of samples, you can have the size of the associated interval that you would expect. Of course, in Bayes nets, we have a ton of random variables, so we need the evidence from sampling the distribution to determine the distribution parameters. So we can sample each variable in turn via the network. I've already talked about the topological order part. Start with the earthquake and the burglary. Go from there, given the values that you generate the value of alarm. From there, generate the probability that John calls and Barry calls. Record the outcome of all 5 of those variables as an example. And then after you've generated 2,000 examples, 20,000 examples, however many examples you do, you can come up with an estimate for the probability of any query that you would want in the network. And the more samples you generated, the more precise that is going to be. The more precise that estimate is going to be. Questions on direct sampling? Does that make sense? If I asked you to write a direct sampler for that Bayes net, would you be able to do it? Like a quick Python script to just take in those associated probability densities and come up with examples and then estimate it? That'd be a fun assignment. Too bad I'm not doing that.
Yeah.
So there is one flaw to this, and I've alluded to it already, in that when there are very unlikely events, it's very difficult. It scales how many samples you need before you have a reasonable sample of the unlikely event. So we can find that there are easy to sample and hard to sample distributions within the same network. So for instance, the probability that John calls and Mary calls, John calls a reasonable amount of the time, even if the alarm isn't going off. Mary calls a fairly reasonable amount of time, multiple times per year, given the alarm is not going off. But the probability of a burglary is so low that it creates kind of an issue. It's hard to sample burglary because even if we generated 1,000 examples, we'd have an average of 1 burglary in those 1,000 examples, as mentioned before. So you can start using rejection sampling, which says that we're only going to generate examples. We're going to throw out any example where what we care about isn't true. So generate them randomly, and if a burglary doesn't happen, immediately throw it out. And that allows us to conditionally test on burglary. Or you can hold it constant and say a burglary is happening, simulate the rest of the network. And that will allow you to further hone your query. So hold as evidence what it is you care about. So you're going to hold that to be true. So a burglary is happening. Burglary equals true. Know that going in, then query the rest of the variables. So reject any samples that don't meet the evidence requirements. So we want to estimate the probability that rain is true, given that sprinkler is true. You just generate the entire distribution, reject anything where sprinkler is false, normalize so that the probability of everything is 1 from everything that was generated, and then you can calculate or estimate any conditional probability from generating those examples. So what if there are many conditional requirements? What happens is we end up rejecting a larger and larger proportion of the generated samples. So imagine I'm curious about the conditional probability that what happens when a burglary happens and an earthquake happens at exactly the same time? How many samples would I need to generate before burglary was true and earthquake was true just once?
What was the odds? 0.00.
It's 0.001 for a burglary and 0.002 for an earthquake.
Yeah.
Multiply. So one is 1 in 10,000. Or 1 in 1,000, and one is 1 in 500. So 1,000 times 500 is 1 in 500,000. You need to generate 500,000 episodes of this in order to have a sample size of 1 for your query of the evidence. In order to get a sample of even 40, that's 500,000 times 40, 20 million examples. That's a lot in order to even have what is considered to be statistically significant, a sample size of 40. That's pretty bad. So it could be thousands or millions of times slower in a particular network. I like this example. How many humans survive when a 1 kilometer diameter asteroid crashes into the Earth? How many days do we need to simulate before this happens even once? So you would need to ignore all days where the event does not happen and then die of old age because it hasn't happened by the time you die. So it's harder to answer those questions that are probabilistically uncommon if you only have the ability to simulate the entire network. It's wonderful if you have the ability to hold some of these variables constant. It's especially nice if they're at the beginning, because then you can hold things like burglary and earthquake true. But how do you hold John calls true when it's at the bottom of the network? You have to start with simulating burglary and earthquake, so you actually have to go through this process of generating an entire sample. You can't just hold John calls true, because we don't know that that's true until we get to that point in the example. So easy to do if it's at the beginning of the topological sort, and difficult if it's at the end of that topological order. So that's rejection sampling. Generate examples, throw out those that don't meet the evidence, normalize. Then there's the challenging one, importance sampling. Anyone heard of importance sampling? I was wondering if that answer, if one person would raise their hand because they saw it in game dev too. So importance sampling is going to utilize one distribution, and then is going to map one distribution onto the other to be able to make claims about the other. So we're going to simulate one distribution through another simulation by looking at the differences between those distributions. Does that by itself make sense?
Trying to find a relationship between the two?
Yeah, it's gonna use the relationship between those two to be able to map one of them onto the other. So creating the new distribution, separate the evidence variables from the non-evidence variables. Keep track of the weight that is those conditional probabilities, and we end up with, I actually wanna read this directly out of the book because I think it does a pretty good job of explaining it. So applying importance sampling to this query, the probability of rain given cloudy is true and wet grass is true. So we know it's cloudy, we know there is wet grass. So what is the probability that the grass became wet because it rained and not from the sprinkler? So we can use any topological ordering. We weight set to 1, we generate an event. So we know that cloudy is an evidence variable with value true. So this allows us to change the associated weight based on the probability of cloudy. We're going to now set it to 0.5. Sprinkler is not an evidence variable, we sample from it. So now we query, what is the probability of sprinkler given that cloudy is true? This is true 10% of the time and false 90% of the time. Let's suppose a random number generator generates false from this, from that associated distribution. Then we move forward, so now we know that sprinkler was false. Rain is not an evidence variable, sample from rain given cloudy is true, that's true 80% of the time and false 20% of the time. Use a random number generator, assume that returns true. That happened 80% of the time, but it returns it true regardless. Wet grass is an evidence variable, we set that to true. So we update the new value of the weight by the associated probability that wet grass is true, sprinkler is false, and rain is true. So we're using the associated conditional probabilities as a way of estimating this new variable's probability. So we use the sampled, kind of the evidence that we're gathering, as a way of approximating the existing one, like transforming it. So now your new weighted sample is going to return this event with some weight. And you would do this for every possible evidence variable. Not evidence, sorry, query variable. There's a lot more unimportant sampling. It's a very large statistical technique and idea that we use in stats. But in general, very useful for sampling from one distribution when you only have access to another. You look like I've slaughtered you. So that's important sampling. When you talk about likelihood weighting, so this is just the algorithmic version of this process. We could ask, given that we're doing this likelihood weighting, so we're figuring out a probability that we can't directly sample by sampling everything else. That's basically what we're doing with this. So as we scale the number of examples, what is the associated error from likelihood sampling versus rejection sampling? If we use rejection sampling, then it's going to take us more and more and more examples, as we have to throw out every time the evidence variables aren't what we're looking for. So we have to generate lots of them. You can see that with rejection sampling, the error does reduce over time, but not particularly quickly, because we are throwing out tons of these examples. With likelihood weighting, where we're using importance sampling instead of rejection sampling, then we very quickly approach no error. Because we can directly sample from what we care about, because we set the evidence variables to what we care about from there. Does that make sense? I never know how well this is going. How are we doing? Feedback time. Yeah,
The projector is uniquely placed so that it's just shining right off the white blackboard or whiteboard, like into my eyes,
Oh,
and
no.
I'm just dying, so. That's where I'm at.
that's fair.
You're saying the center.
But I sit off center.
Yeah,
I have one more.
yeah, it's the center that gets the.
I can see.
It's worse if I turn these lights on.
Yeah, no.
I don't know if it's actually worse, I think we need to take more samples.
There we go.
Near range.
Yeah, so likelihood weighting is just using rejection sampling where we already are throwing out the examples because we're directly being able to sample from it by sampling from the distribution that we already have. It's the equivalent of just saying we can hold those evidence variables constant, and we hold them constant by using the importance sampling ratio.
Just like multiplying each one of them by a weight that you made up and then.
So you don't necessarily make it up, you sample directly from it and hold your evidence variables true, so that every single example that you're getting is relevant. You can see that this top chart is basically embedded in, you can't see my mouse. This here is basically what that there is. So the entirety of this graph is embedded in this small chunk of this graph. So we get this value by the time we've reached this, and it's even better than that at that time, but we're throwing out lots of examples here, and every single example has value here.
Is there, how did you get the relationship? Or was there an equation for it, or was it just measured exactly?
Yeah, I believe it's measured exactly from something that this does come from the book.
Yeah.
But yeah, it's based on some problem that the data was gathered directly from.
Is there a way to know the number of samples?
That it's going to take.
Yeah.
Yeah, so there is a statistical way to do that. Generally, 40 examples tends to be statistically significant. By the time you see something 40 times sample from it, it approaches the true distribution, assuming that it's normally distributed. At least you can use the central limit theorem to force that into it. But if you're not doing that, then you have to think about, all right, I want 40 samples for every possible condition. So if you're branching and asking, all right, here are the evidence variables. So we want to figure out there's a query variable, there are the evidence variables that we're holding constant, and there's every other variable. You want there to be a sample size of 40 down each of these paths.
That's 40 times. the number of
Well, it depends on the associated probability, because you might not be equally likely to end up on each of these.
Oh, I see.
So if you're using rejection sampling, for instance, then if one of these is true only one thousandth of the time, then you would need 40,000 examples to have a sample size of 40 down here. So it's going to be based on the least likely variable. But if you use likelihood weighting, then it doesn't take, you can factor that out. Instead of taking 40,000, it would take 1,000. I'm sorry, just take 40. You'd be able to immediately bin, let's get a 40 sample directly here, 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 and here. So you can directly sample exactly what you want, as long as you set it up to be able to sample based on, you set the new evidence variables the way that you want them, so that you can, this is just a conditional probability, this is a conditional probability, this is a conditional probability. So you set the likelihood weighting, holding everything else constant, and then you can directly sample from it. really good question. Other questions? Likelihood weighting is nice, but it's a little bit harder to set up. So that's direct sampling, where we're going directly from the evidence. We're querying the distribution itself, and we're starting with a new example every single time. So that is direct sampling. On the other hand, we can use a Markov chain. And the way you can set this up with a Markov chain is that we generate an example, and then we make single changes to the last example as a way of generating the new example. And we end up with an agent that explores the space with the associated probabilities of being in that space. So you can imagine that we have an example where there was no burglary, no earthquake, no alarm, John called and Mary did not call. We could make an associated change to this state by flipping one of the variables to sample from. But we would do this with proportion to how likely each of those variables would be to flip. So we're going to use what's called Gibbs sampling to do that, if anyone's heard of the concept of Gibbs sampling. So yeah, start with an arbitrary state. We'll just initialize the variables randomly. Any evidence variables? So if you're trying to sample from this where John calls is true, you would set John calls to true and then randomly set the other variables. Then you would generate a successor state by randomly sampling one of the non-evidence variables. So again, John calls. So let's say we set John calls to be true. Let's generate, we said, not burglary, not earthquake, not alarm, John calls, Mary does not call. So this is our evidence variable. We can't touch that because we want to simulate what is the probability of something else given that John calls. So we hold this constant, but now we can query any of these other variables. We're going to select one of them at random, and then we're going to sample from its distribution. So let's say we randomly select burglary. We are then going to sample. The chance of burglary is 1 in 1,000. So 1 in 1,000 times, we are going to change this to true. 999 times out of 1,000, we're going to keep it false. And that generates the next example. Then we pick another variable. We randomly pick earthquake. 2 out of 1,000 times, this changes to true. 998 times out of 1,000, it stays false. Continue to do that by randomly selecting one of these variables to change, and then you sample from that. Question?
Yeah, this, your earlier what you're saying was based on how likely it was to happen, that's what you put, or is that for something else?
It chooses it randomly, but the chance that it flips is based on how likely it is. So the new value that it takes. Do note that if I flip burglary and it's true, I have to reselect burglary again. It's going to continue to be true while I select earthquake and Mary and earthquake again and alarm until I reselect burglary, and then it's very likely to be false again.
So when does infer bias though?
What is what? Sorry?
Infer bias.
It actually doesn't in the big picture.
I don't understand that.
We can show that a Gibbs sampler with a large enough sample size will converge to the associated probabilities of a larger network.
But it has to be written some sort of. I doubt like anybody would, like if you wrote something that included this technique in it to basically have an outcome or not an outcome, but to affect a variable, an independent variable, and have manipulated. Like you would have to at least note that it's not completely random. It's not.
Yes, it is not, well, anything is not completely random, but in this case, the more samples you gain from this, the closer it gets to the associated true probability. So if you wanted to figure out what is the probability of burglary given that John called, for instance, you could, we'll start with this random example. Then we record that this happened once. Then we would, with probability Let's actually go through an example of this. So someone use a random number generator and select something between 1 and 4. It's not random. Someone use an actual random number generator.
They are random number generators.
Yo, I second that. 6.
Between 1 and 4?
Yes. And-
Flip a coin twice and do binary.
2. So now I need a random number between 1 and 1,000, where 1 and 2 are going to be true and anything else is false.
Oh,
Between 1 and 1,000, random number.
I have 680.
Perfect, false. So the next example is going to be not B, not E, not A, J, and not M. So now we have a second sample with this being true. All right, let's restart. Random number between 1 and 4.
2.
4.
4. I only trust Christopher. The only one who actually looks to be
Chris bias though?
Interesting.
totally different name, Christopher.
Very
The diff returns true. So now we need to figure out the probability of Mary given these. We actually have to instantiate and look up in the network. What is the probability that Mary does or does not call, given that this was false, this was false, this was false? So what is and I need to have access to it to be able to do it, but you would look up the probability in the alarm table where burglary and earthquake were both false. Then from there, you would say alarm is not true. So what is the probability that Mary calls given that alarm was false? So we really only care about that. Mary only cares about the alarm. The alarm was false. So what is the probability that Mary calls given that alarm was false? I think it was 0.01 and 0.99. I think so. We'll go with that. If it isn't true, then it isn't true. So Mary calls 1% of the time when the alarm doesn't go off, and 99% of the time she doesn't care. So in this case, we would want to sample random number between 1 and 100. 1 is true, 99 is false. Someone, anyone?
20.
20, so this stays false. So we generate it again. And it's because I started with such a likely example, and because this network is very unlikely to be true, very unlikely to be true, very unlikely to be false, given that this was false. When this flips to true, then the associated probabilities change. And you can see that with a large enough sample, this random walk in this space would actually approximate the full distribution. And we can talk about why, but that's exactly how that process would work. You're using a Markov chain now. You're using the last example, and you're making one change, one random sampling of one variable from that. And you need a larger sample for that to generalize, but it's also a lot less expensive to make one associated change than to go through the entire network and set every single variable based on its associated probabilities. So you can generate examples faster with Gibbs sampling. So given the same amount of time, you can come up with 4 times, 5 times, 40 times more examples because you're only making one change instead of redoing everything. So this is the idea of Gibbs sampling. One other way to visualize this is you imagine the state space of every non-evidence variable, so non-John calls. There were 4 non-evidence variables in this case, so there would be 4 dimensions, and the point that we are in is in that 4-dimensional space somewhere. The equivalence of Gibbs sampling is saying pick a dimension, and we're going to sample and change that dimension based on the associated function that defines that given where we are in the 3-dimensional space that's outside of that. Maybe this works in fewer dimensions, but let's draw maybe we'll draw a 2-dimensional space and say we have some function in that 2-dimensional space. What do I want to draw? Some function in that 2-dimensional space. And if where we are is, but it needs to be a density function. So It's going to. I'm gonna draw it, yes. I'm just gonna draw this as true false. That works better. So in a two-dimensional space, we now choose randomly variable 1 or variable 2. Let's say that we are currently right here. We choose variable 1 or variable 2. We randomly pick variable 1. We will resample this space, and we can possibly hop from here to here. Or stay here. Let's say we stay here. We randomly choose again. We choose variable 2. We resample this distribution given that V1 is true. So you can see how what we're sampling is we choose one dimension and we're taking a walk in one of those dimensions by resampling that distribution. But what if the associated probabilities, if we draw this out as a conditional probability table, let's draw out something that is likely. So let's say variable 1 is variable 2, we would need on the other axis. Something like this. So given that we are somewhere, where is the most likely place to be in this graph? Top left? Yeah. How hard is it going to be to move from this top left square? If we choose variable 1, then this 0.8 needs to be 20% of the time we're moving in this direction. If we choose this, then 10% of the time we're moving here. So we see that we're going to be generating a lot of examples up here, but that makes a lot of sense because in general, if we were to query what is the value of variable 1, what is the value of variable 2 in this, we're going to find true happening most of the time. So we see that when we Gibbs sample, we're actually sampling from the more likely events more frequently and the less likely events less frequently, which is exactly the same as you would otherwise. Even if you end up somewhere like here, how likely are we to move up or move left? Fairly likely. How likely are we to move left when we generate this? Very likely. So we basically have kind of a magnet to the most likely event over here that's drawing us toward that in some capacity. And when we stay there, we don't necessarily escape particularly easily. But if you don't believe me, write a program that simulates something like this, and then figure out how frequently you end up in this square, this square, this square, and this square by doing Gibbs sampling versus direct sampling, and you will find the exact same probability over the big picture. It doesn't matter if you pick a value for variable 1 and then pick a value for variable 2, or if you are in a particular space and you sample one dimension or the other. You get the same probability distribution in the big picture. Questions on that? We've been here for a long time. All right. So yeah, this is called Markov chain Monte Carlo, or MCMC for short. And we just pick a dimension, move somewhere in that dimension. Yeah, given infinite sampling converges to the true conditional probabilities, which is really cool. It's also way easier to implement and is guaranteed to be constant time to generate the next example, rather than linear with respect to the number of variables. So you can shave a dimension off of your sampling. I'll give you another example. because I like examples. So we're gonna go back to our rainy, sprinkler, cloudy world in some capacity. So we can generate what looks like a markup chain from this. So you're gonna be in one of these states, and we, with some probability, make the associated transitions between these particular states. So evidence variables for sprinkler and wet grass are fixed because we know that to be true in the query. What is the probability of rain given sprinkler is true and wet grass is true? So sprinkler held to be true, wet grass held to be true. The non-evidence variables of cloudy and rainy are going to be part of our markup chain here. And we're just going to now sample this graph. There's a probability that we stay where we are. There's a probability that we move in the cloudy dimension, and there's a probability we move in the rainy dimension. From here, we can start to see why this works really well. You're just infinitely taking paths from here to here to here to there, here. I guess that's reasonably likely, that's likely, that's likely. Maybe we do that, we do this, we do that, we do this, that. You can see that we explore that space, and with a large enough sample, then the chance that we end up where the distribution approximates the true distribution. If we did this 1,000,000 times, 1,000,000,000 times. So what's super nice about this, just proportional to the number of children, rather than the entire Bayesian network, which is great. And information propagates from the evidence nodes in all directions, which is great. So it's complete because of that. So when the evidence is toward the end of the network, this ends up being very nice because we can easily sample from the rest of the network. But if the evidence is toward the beginning of the network, then we end up having to conditionally query to get all the way to the end of the network to be able to sample from that. And that becomes a little bit more challenging, but Gibbs will save you a lot of space if the evidence is toward the end of the network. You can ignore those nodes, and then you're sampling from things that aren't topologically at the bottom of the network. So we can find that even if we can, so here's when it's effective and when it's not. The car insurance network, the standard query on property cost and age. You can see that one is toward the beginning of the network, one is toward the end of the network, and as such, likelihood weighting was better on one, and Gibbs sampling was better on the other. So the reason we care about both likelihood weighting and Gibbs sampling is that depending on where it is in the network, you end up with a more efficient network. The ability to query from the network faster. Another question you might have is how long does it take for Gibbs sampling to actually converge? So it rains if and only if it's cloudy. Then we end up with this convergence property. However, the only two joint states that have non-zero probability for cloudy and rain are true, true, and false, false. And that means that it becomes stuck when it reaches one. It never generates the intermediary state. So kind of like with local search, you can imagine where if you did this once, imagine a local search where we have something that looks completely bimodal. So there's no way to sample from both of these. You would immediately hill climb to one peak and kind of be done at that point. That's the same with sampling this network. Even though this is the true probability, you would only, in that network, let's actually go back and look at it on the other slide because it's actually there. this. We're talking about this network now. Where once we are here, we have a probability of 1 of staying here, and we can't generate this intermediary state to be able to half the time get over here. If we're here, half the time we go here and half the time we go here. But once we're in one of these corner states, we stay there for sure. If that's the case, then we can't use Gibbs sampling to sample how likely is it that we end up here, et cetera. So we have to restart the entire process, generate a new random state, and every once in a while we'll generate this state so that we can actually sample going here and going here. So there are times when there are 0 probabilities that Gibbs sampling does not function, and you have to use kind of like a rapid restart from our local search. Be able to do that. Yeah, I guess I could have shown this, is that I did copy it, I was smart. Yeah, sample multiple variables simultaneously or generate successor states more intelligent. All right, we gotta get out of here. I'm fading too, if that's not obvious. So remember, no class on Thursday. I will generate some practice problems and put something on Canvas so that you can get some practice with some of these problems, some of these types of problems. And then Veterans Day next Tuesday, so we'll come back on Thursday. My plan is to probably extend the current assignments, since I think I have that due Monday. Since we're not meeting until Thursday, there's really no reason to have you turn that in before we meet again. So let's just go ahead and say that that's going to be due Wednesday, ahead of our next Thursday meeting. I will get a study guide to you by Thursday.
Yes.